I've already received some of your labs. If you've got that, I'll take it after class. You can hand it to me, or remember that you can take up until the beginning of the final exam. All I need for that is for you to calculate the K values, filling it into that table, and then attach supporting calculations that shows how you calculate those K values. I'm sorry we didn't get a chance to do more of the fittings. If I hadn't been running around with the N2 students in the hour before our lab, I maybe would have been able to clear the sediment out of some more of those taps. But hopefully you got the idea that local losses are a way of having a pressure reduction through a pipeline, and depending on how many you've got, it's important to keep track of them and not just neglect them. Your final exam is Thursday the 11th, so that's a week from today. You'll be halfway through the exam already. You can prepare a one-page equation sheet, and the exam is comprehensive with added emphasis on Chapter 8 and Chapter 7. So the first two midterm exams covered Chapters 2 through 6, and all of that is going to be included, but in less detail, and there will be less point value associated with the questions that come from the older materials. So that's what I mean by it's comprehensive with added emphasis on the newer material. All right, we're going to talk about dimensional analysis and similitude. And to begin that, there is a phrase that I need to clue you in on, and that's an equation being dimensionally homogeneous. And so consider this equation, which is the equation of flow over a weir. It's an equation that we'll get some exposure to next semester in hydraulic engineering. So if the equations on both sides, if the units on both sides of the equation are the same, then the equation is called dimensionally homogeneous. And so we know that flow rate is cubic meters per second, or as it's expressed down here, length cubed. So length is the unit of meters, and then time, when we're saying seconds, that's where the time comes in. So length cubed per time. So we want to see if the units that are on the left-hand side of the equation match the units that are on the right-hand side of the equation. So let's just go through it step by step. This fraction 2/3 has no units. A C value is likewise unitless. It's just an energy coefficient that doesn't have units. But L, it's talking about the actual length of a weir, would normally be measured in meters. And so it has units of length, obviously. 2G, now the G is in the square root. And so it's the square root of length per time squared. So meters per second squared. So when we have the effect of that square root, it's like length to the 1/2 power, and the square root of time squared is just going to be time. And now finally, h to the 3/2 power. That's h that's talking about the height of water above some sharp-crested weir. So we're taking units of length to the 3/2 power. So does it end up being length cubed per time? It does, because we're looking for 3 lengths. Here's 1.5. Here's a half that makes 2 added together, and here's 3, and then the time was in the denominator. So this is a dimensionally homogeneous equation. Let me give you an example of an equation that's not dimensionally homogeneous. In hydrology, if you end up taking the 433 course, you'll see that there is something called the rational method, and it's a very easy way of estimating the flow that will come out of a watershed. So a parking lot, for example, if you are putting in a new business like Cookout. Anybody been to Cookout yet? I ate there within 1 hour of them opening. I'm so proud of that. Like, my spidey senses were tingling. I could taste. I love that food so much I can like taste it before I even know I'm going to eat it. Yeah, I've had 2 meals there already. But anyways, they have a really unusual parking lot. When you walk through their parking lot, you'll say, something's wrong with this asphalt. This asphalt's weird. It's because it's actually porous pavement. Most places don't have porous pavement, but they opted for putting in a porous pavement to try and reduce the amount of water that comes off of that parking lot when it rains. In a place that doesn't have porous pavement, though, let's say you wanted to find out what the runoff is going to be. So this rational method says the flow rate coming out of a parking lot is related to some runoff coefficient C, the intensity of the rainfall, and the area of the watershed. And so let's look and see if the units are dimensionally homogeneous. The way the rational method works is you get cubic feet per second. This runoff coefficient is just a fraction, so it's unitless, so we don't have any units associated with that. The intensity of the storm that you put in is inches per hour, and then you're going to multiply that by the area in acres. And so is an inch acre per hour the same as a cubic foot per second? It's not. It's not the same. Actually, it's close. If you actually do the conversion, you only have to multiply it by 1.008, and then it does turn into cubic feet per second. So most of the time, they just ignore the 1.008, and by coincidence, it works out that inch acres per hour is pretty close to cubic feet per second. So it's not dimensionally homogeneous, strictly speaking, but the units just sort of work out by dumb luck. So that's an example of dimensionally homogeneous, and dimensionally homogeneous equations are usually fundamental equations. They're based on the fundamental forces, just the basics of science and physics, whereas non-dimensionally homogeneous equations are more empirical in nature, which means that these equations have been generated by curve fitting. If you have input data and output data, and there's just a scatter plot, and you find some line that approximates what that scatter plot looks like, that's an empirical equation. You know, this equation where you tell Excel, you know, y equals mx plus b. You say, Excel, give me this equation. Excel isn't examining Newton's second law or, you know, anything in the fundamentals of physics to know what the relationship between the input and the output data is. However, and so that's an empirical equation. A fundamental equation, this is based on a knowledge of how the universe actually works. And so more often you'll see dimensionally homogeneous equations associated with those that are fundamental in nature. So dimensional analysis is a procedure that we can go through in order to do testing with small-scale models that are a lot cheaper to produce than full-size prototypes. We want to simulate the behavior of a full-size prototype with a small model. So if you think about what happens in a wind tunnel with a model airplane, you may have noticed if you've flown recently, it seems like maybe 5 or 10 years ago they started putting tips on the ends of wings. Have you ever seen those tips? They point up at the end of the wing like that. Well, recently they're starting to put tips under the wing as well. They're smaller usually, and they sort of are angled out. But at some of the larger planes, they put these little winglets at the end, and it's a way of actually trying to enhance how laminar the flow is over the wing and trying to reduce turbulence and make the plane more fuel efficient. But the way that they came up with the idea of whether to use winglets or not is by tests in a wind tunnel where they have some mock-up of a small size airplane made out of clay or wood or whatever they can shape easily. They put it in the wind tunnel and then they measure the drag. They do visualization of the flow. They'll have wind going through there, and they'll maybe add some particles like a very fine dust, and then with a high-speed camera track those dust particles so they can see where the particles are going as an indication of what the flow inside of the wind tunnel is doing. So dimensional analysis is a numerical tool that we use in order to interpret model data. Here's a picture of a really interesting and cool physical model that's in San Francisco. This was built in the 1950s to test a proposal that had been made. There was an engineer who proposed actually damming the entire San Francisco Bay. The idea being that if they put in 2 dams, they could make the bay freshwater. It would be this enormous reservoir of water that could be used for irrigation, and so nobody knew what that would do to the surrounding area. And you know, back in those days, they sort of acted first and asked questions later. That was sort of how things went, environmentally speaking. You know, they would dump a chemical onto the ground and maybe 20 or 30 years later start asking if it was a dangerous chemical. But contrary to that more general trend, quite fortunately for the Bay Area, people were asking questions: what would be the effect if we put these dams in? How is it going to change the ecological balance? How is it going to change the flow patterns inside of the bay? And so they built a very, very large mock-up that was in use for a lot of years. When they built the mock-up, it quickly became apparent it would be a terrible idea to put those dams in. It would totally change the flow patterns inside the bay. It would kill off large species of fish. It would ruin a lot of habitat area for migratory birds. Here's another video. Here's another look at it. The model itself, as it said on the previous slide, is 320 feet wide and 400 feet long. So it's, you know, I don't know, that's larger than a football field, right? And so let's just watch a brief video tour of this to give you an idea of what can be accomplished with physical modeling and the interpretation of that physical modeling in the form of dimensional analysis. I'm going to watch a commercial first, I guess.
It's knowing that your door is always open and your path is free to walk.
All right, I'm sure that we'll all go out and
We're here in the San Francisco Bay Model Visitor Center, where you have a chance to see the only operational hydraulic working model in the United States today. The primary purpose in building the model was to test the John Reber plan. John Reber wanted to dam the bay. He wanted to build 2 freshwater reservoirs by constructing 2 large dams, one where the Bay Bridge is and one where the San Rafael-Richmond Bridge is. After the construction of the Bay model from 54 to 57 and all the tests of his theory and his idea, it was summarily rejected. Fortunate for all of us, or we probably wouldn't have a San Francisco Bay today. After the construction of the model, it was used as a scientific operational research test facility from 1954 until January of 2000. Scientists could predict impacts on oil spills, major storms, but mostly the impact of man-made projects on any part of the shoreline. The San Francisco Bay model represents about 1,600 square miles of land and water resources, about 70 miles inland from the coast of California. The Pacific Ocean is built all on sand, but the entire rest of the model and the delta are built out of concrete slabs. There's about 286 of them. They're 12-foot squares. They weigh about 7 tons each, and they're all elevated about 30 to 38 inches up off of the floor. We have 2 supercomputers and also a lot of very sophisticated technology in a little facility called the Tide Hut. Every morning when we turn on the computer, it takes about 20 to 21 minutes to flood the entire model and the delta with about 135,000 gallons of water. At the end of the day at 4 o'clock when we close to the public, we close the system down. All the water drains back into the sump tank. You'll see throughout the model there's about 250,000 copper tabs. They're embedded in the concrete, and their primary purpose is to help provide frictional resistance to help create the right tides and currents. There's 3 specific criteria that are important in analyzing how the model is calibrated and how it operates. The horizontal scale of the model is 1,000 to 1. So for every 1,000 feet underneath the Golden Gate Bridge, 1 foot in the model. The vertical scale is 100 to 1. So for every 100 feet underneath the Golden Gate Bridge, 1 foot down in the model. But the most important factor is time. Now a lunar day is like 24 hours, 54 minutes, so many seconds. But in the Bay model, that happens every 14.9 minutes. So every 14.9 minutes in the Bay model, you have 2 high tides and 2 low tides. Mathematically, it's changing about every 3.78 minutes. The area of the Bay Model, what we call the San Francisco Bay Model Delta area, this represents about 1,600 square miles. It's about the size of the state of Rhode Island. When you're standing on our observation deck looking down at the Bay Model, it's about the same as flying in an aircraft above the city of San Francisco at an altitude of about 10 to 12,000 feet looking down at the bay.
All right, so that gives you an idea of how physical experimentation can be used to answer engineering questions. That's the only full-scale operational model of its kind in the United States, but the Army Corps of Engineers has physical models of spillways, of dams, and so this isn't the only place they do physical experimentation. It's actually a pretty common procedure, although it's becoming less common than it used to be because of the advance of numerical methods. So let me show you what's sort of replacing physical experimentation in terms of being more common is computer simulations. And this is a simulation of a dam, and it predicts how sediment downstream of the dam is going to be picked up. When there's a high velocity water coming over the spillway of the dam, there's a lot of energy there, and that energy can scour the stream bed. And it can be actually quite damaging to a stream to have high velocity water scouring it. And so these computerized numerical models are breaking the flow field up into tiny little elements. And so that's why physical models are a little bit less common than they used to be, is because with computing it's possible to simulate a physical environment without having to build anything at all. And it can be obviously quite costly to construct and operate a physical model like this. They were talking about the geometric similitude of that model, how on the horizontal scale it's 1,000 to 1 and on the vertical scale it's 100 to 1. So similitude is saying that there's a relationship between the prototype and the model. In the Bay model, the prototype is the San Francisco Bay and the model is what they've got at that indoor facility. Well, we can have prototypes and models for cars, for airplanes, for boats, and one of the examples I like to use is a little Matchbox car. And it seems like everybody had little toy model cars when you're growing up. You can buy them for like $1 at Walmart. But they don't behave like a real car. If you think about dropping a model like a Matchbox car, you drop it from shoulder height onto the ground, there's nothing going to happen. You just pick it up and there's no dents. It hasn't exploded. You know, the windshield didn't shatter. Nobody's falling out of there all bloody. But think about like a real car. If it was lifted to an equivalent height and dropped, I mean, you've probably seen something like that on Mythbusters, right? They'll drop a car with a crane from 10 or 15 feet and it falls apart. It's like it was never a vehicle at all, how much it falls apart. And so you know that just because you've got an exact geometric replica doesn't necessarily mean that the model and the prototype are going to behave similarly. So I can have a small boat like this that in every detail matches, but scaled down, in every detail matches the full-size prototype, but we have to go beyond geometric similitude and try and find some way to scale the forces and the effective forces. And so that's what dynamic similitude is. It's a little bit more complicated than just scaling everything down by a factor of 1,000 to 1. And in dynamic similitude, you have to ask, how is this model going to be interacting with the liquids or the other moving parts that are that we're trying to simulate? And so you can see that a model spillway is going to have a thinner layer of water going over the front of it, but it's the same liquid. You can't scale down the water molecules 1,000 to 1. It's the same H2O, so sort of like you scaled everything except for the air and the water that is going to be interacting with the model. And so you have to somehow correct for that. And one of the common ways of doing that is making it so that the Reynolds number associated with flow over the model is matching the Reynolds number of the flow of the prototype. And so let's just jump straight to the chase with an example of what if we were going to be trying to simulate the behavior of a full-size Goodyear blimp, and we had a smaller size model, a 10-to-1 model. How would we test that model so that it's going to accurately predict what happens with the prototype? This is going to illustrate what you have to do in order to make sure that dynamic similitude is satisfied. In dynamic similitude, you have to match the Reynolds number. So we're going to have that the Reynolds number of the model equals the Reynolds number of the prototype. The equation for the Reynolds number is the velocity of the liquid, a length parameter, density divided by the viscosity of the fluid. And so we're going to make sure that the velocity of the air going around the model multiplied by whatever length parameter of the model multiplied by the density of the fluid used with the model divided by the viscosity of the fluid used for the model is equal to all of those parameters for the prototype. So V sub P times L sub P, density sub P, and viscosity sub P. So some of these variables are associated with the fluid, and some of the variables are associated with the model. The length parameter, for example, we're talking about the size of the model. But all of these others are the fluid. It's going to be the velocity of the fluid that's running past the model. So it's in some sort of a wind tunnel. We'll have, we want to know, in this case, if the prototype is flying at 10 meters per second, what velocity should we use in the wind tunnel to get an equivalent ratio of forces? So we are wanting to find here what is the velocity that's going to use in testing the model. And so we just rearranged the equivalence of the Reynolds number to solve for V sub m. So it is V sub p, L sub p, density sub p, viscosity sub m, divided by viscosity sub p, length sub m, and density sub m. So just rearrange the viscosity to the numerator here, and the length and the density into the denominator on the other side there. And that gives us the velocity of the model. So we account for all of those things. We have some of the things that are going to be the same, though. If we're using air for the model and prototype, then the density of the model fluid and the density of the prototype fluid are equal. And also the viscosity of the model fluid is equal to the viscosity of the prototype fluid. So we don't need to put in any different value if we're using air in both situations. Okay? So we'll say cancel out the density term and the viscosity term, since the fluid in both cases is air. So what we're left with is the velocity of the model is going to be the velocity of the prototype. Prototype will be 10 meters per second. And now the ratio of the length of the prototype to the length of the model. The prototype has 10 units of length for every 1 unit of length for the model, because it's a 10-to-1 model, it says in the problem statement here. So what that means is that we have to have 100 meters per second is the airspeed in the wind tunnel. So who can think of like a logical reason why, if the model is smaller, why do you have to have faster moving air in order to have dynamic similitude. I mean, it's a little bit counterintuitive, isn't it? You'd maybe think that if you're making the model smaller, then it should be that the wind is going to be less. But this is telling you actually you need to have 10 times as much air going past that model if the model is 1/10 the size. So anybody want to take a stab at explaining why that is? All right. It's partly about friction. It's important to think in terms of forces, really, though. Remember we were talking about that Matchbox car and how it doesn't seem to dent as easily as a real car would. Things get stronger when they're smaller. I don't know how to explain it other than that. Since the model is smaller, it holds together more easily, and so we have to apply heavier forces to it. So 100 meters per second. If we wanted to know, for example, this blimp, when it flies, the wind sort of changes the shape of it. It kind of gets smashed a little bit because it's somewhat flexible. So the wind blowing on the front of it makes it compress ever so slightly. So what would we have to do to get that smaller model, which is stronger because it's scaled down and so the span between support beams is less? Maybe that's a way of thinking of why it's stronger is, if you're walking over a roof and the supports for the roof are 10 feet apart, the roof may collapse when you're in between supports. But if the supports are closer together, then there's less likelihood that it's going to collapse. And the same thing is true with this small-scale model, is that inside a blimp, there is structural steel that forms a frame, and this fabric goes over the frame. And so in the prototype, the structural steel is shrunken down, but there's less of an unsupported area between those structural steel elements. And so you have to have more wind going into that smaller scale model in order to have the same ratio of forces. So, from just sort of a logical, physical perspective, trying to understand and accept the numerical side of things, I think that may help to explain it. Any questions about the idea of dynamic similitude? I had a classmate when I was in graduate school that had to do tons of this stuff for his master's degree. Dimensional analysis really saved him a lot of time because he was doing tests on how water flows through different parts of a drinking water treatment plant. You probably know that drinking water is chlorinated, and that's what gives it sort of the terrible flavor. You can really taste it. Those students from Mexico that were visiting on Tuesday, one of the things they mentioned when I told them that I teach classes related to water, they said, boy, the big difference between drinking water here and Mexico is it tastes like chlorine, and the water here tastes like chlorine. And I didn't mention it, but that's part of the reason why you can drink the water here without getting sick, is that it tastes bad, but I'd rather have chlorinated water and not get Montezuma's revenge. But anyway, this graduate school colleague of mine, what he was doing, instead of chlorine, another way of disinfecting water is you shine ultraviolet light on the water, and then it kills viruses and bacteria, spores. The UV radiation will. And so he was modeling how does water flow through this UV reactor. And he was able to do a lot of dynamic similitude. Instead of having to do full-scale mock-ups, he was able to use smaller prototypes, and so it saved him a lot of time. So here's another one. I'd like you to try this on your own, using the same, making the Reynolds number match. Okay, we've got water flowing through pipes. Oil is flowing through a smooth pipe that has a diameter of 15 centimeters, and we want to know if we were going to try and model a water pipe, a 5-centimeter water pipe with this oil pipe, then what velocity is it going to be going through the water pipe? What's the equivalent velocity? So I will stop talking and give you a chance to calculate that. Of course, you can all right, we can write Reynolds number in this alternate way if we know both the density and the absolute viscosity of the fluid, then we can substitute kinematic viscosity, because the kinematic viscosity is the absolute viscosity divided by density of the fluid. So that's where Reynolds number as the velocity diameter divided by kinematic viscosity comes from. So what we want to do is we want to have the velocity of the oil flow times the diameter of the oil pipe divided by the viscosity, the kinematic viscosity of the oil, match up with the velocity of the water pipe times the diameter of the water pipe divided by the kinematic viscosity of the water pipe. So velocity of the water pipe is going to be kinematic viscosity water, velocity oil, diameter oil, divided by kinematic viscosity oil, diameter water. Okay, so those values are 1 times 10 to the minus 6th, which is typical velocity of typical kinematic viscosity of water, 10 to minus 6 meters squared per second. It's the standard kinematic viscosity for water. The velocity of the oil, 2 meters per second. And then the diameter of the oil, it's a 15 centimeter pipe. We don't have to switch that from centimeters into meters, because the diameter here is also going to be in centimeters, and so the units will cancel out. You can switch if you want, but it isn't necessary because it's all going to cancel out. The velocity, the viscosity of the oil, kinematic viscosity of the oil is 4 times 10 to the minus 6th meters squared per second. And then the diameter of the water pipe is 5 centimeters. So the velocity of the water through the pipe, to have it match up, is going to be 1.5 meters per second. Think about the blimp. We had to have a really high fluid velocity through the wind tunnel to get the forces high enough on the blimp. 100 meters per second may be tough to achieve. But what if, instead of using air at 100 meters per second, what if we could flood the wind tunnel with a liquid? Then that would allow us to achieve the forces that are required without having to have such a high velocity. Because, you know, if you use a fluid with a greater density, then you're not going to have the fluid moving nearly as fast to have the same force or friction on that blimp. So that's something that's sometimes used is, you know, when you're playing around with making the dynamic similitude match up, you've got a lot that you can change. You can try and find a fluid with a different density. It's not just the length parameters and the velocities that can be controlled, but you can also use an alternate fluid as well. So that's enough about, for now, similitude. It's something that we could spend a whole semester on similitude, but we're going to change gears a little bit to the more esoteric side of dimensional analysis. It's kind of, in a way, what I'm going to be showing you now is a little bit like a puzzle. It's like a brain teaser. And the brain teaser arises from the need to generate new equations. Maybe you've wondered the same thing as me. Sometimes you go through a textbook and it's got all of these equations, and you think, how did they figure out? Was it just dumb luck that, you know, this equation that has 10 variables in it, they figured out that it was, you know, this variable's in the numerator and it should be to the 1/2 power, this variable's in the denominator to the 3/2 power. It's like, where do those equations come from? And one of the tools that can guide the creation of new equations to describe the behavior of physical systems is dimensional analysis. And so take, for example, water flowing through a pipe, but then there is an orifice inside of the pipe, and it's actually, the orifice is pointed counter to flow. So this is sort of like a donut shape. There's a ring on the inside of a pipe. Well, what if we wanted an equation to say how the fluid is going to behave in an orifice that's enclosed inside of a pipe? Well, we can use the same numerical models, like I showed you that spillway model. We can use those numerical models to simulate what happens inside of there. But sometimes they are not really accurate unless they've encountered and have been programmed and calibrated to a situation like this. And so, you know, you can't have a computer just and assume it's going to be able to always give you an accurate result. And so you have to verify that with physical testing. And you can't always do full-size testing, so it's the small-scale models that are used. So let me tell you about dimensional analysis. There's a process called pi groups. It's generating a pi group is a unitless parameter that allows you to know if there's a whole list of variables that are somehow related to predicting a parameter, like what the drag force will be, then you can rearrange the variables to try and find what the equation is according to developing pi groups. And so a pi group is a unitless parameter. And so just take Reynolds number, for example. We've just been calculating Reynolds number here with dynamic similitude. Reynolds number is a unitless quantity. And if we look at the units of the Reynolds number, it's unitless because density, for example. Density has units of mass per length cubed. And if you consider velocity, that's length per time. And then the length parameter is length. Well, viscosity, if you expand out all of the units, where newtons can't just be expressed directly in terms of mass, length, and time. Because if you get down to it, every variable is just some combination of mass, length, and time. Those are the three master units that everything else is made out of. So length, mass, and time are the base units. So here, if you convert from newtons to kilogram meter per second squared, those units can be expressed in terms of mass, length, and time. And the others already are if it's a newton second per meter squared. So if you get the units of viscosity, then it's mass, length, time. Combine them all together, then it's a unitless. And the way that it's sometimes expressed in textbook, you know, a unitless quantity they just say 1 to mean that there are no units. Or if it's a 0 in brackets in other textbooks, that's another way that they somehow say that something has no units. And so Reynolds number is an example of a dimensionless quantity. And the Buckingham pi theorem is a way of combining lots of different variables together in order to generate these unitless quantities. If you identify pi groups, then that'll help you to know what the equation is that relates behavior together. So let me give you an example of if you have spheres that are falling through a fluid. You do physical testing. Let's say you went into the lab and you observed that you had a lot of different spheres, and if you changed the diameter of the sphere, then the drag force went up. You didn't know exactly what the relationship was between diameter and drag force, but you knew that the drag force was dependent on the diameter of this sphere that's falling downward through a fluid. You also knew that if you changed the viscosity of the fluid, that also changed the drag force. If it was falling through water, then it would fall at a different speed than if it's falling through a thick, viscous oil. So you, through lots of different testing, identified that each one of these properties had some effect on the drag force experienced by the particle, but you didn't know exactly how everything combines together. So in the Buckingham pi theorem, the analysis starts by identifying how many variables there are that are related. And you'll notice that there are 5 variables that have been previously mentioned. There's the drag force, the velocity, density, viscosity, and diameter. So 5 variables and 3 basic dimensions, meaning each of these can be broken down into having units of length, mass, and time. And so the difference between there being 5 variables and 3 basic dimensions means that we should be able to combine all of these variables together and form 2 groups that are both unitless. And it's those two unitless groups that would be used to generate the equation that relates the drag force and all the other parameters. So let me show you what that process looks like. This is going to be pretty weird and abstract at first, but I think you'll catch on quickly. Let's start with force. Force is units of newtons, which is a kilogram meter per second squared. So that is units of mass, length per time squared. Okay, consider velocity. We usually say velocity in terms of meters per second. So that's length per time. Viscosity is newton seconds per meter squared, which is the same as a kilogram meter per second squared. That comes from the newtons. And then there's still the seconds and the meters squared that were there before we expanded out the newtons. So if we reduce all of that down by canceling out the seconds here and that, and the meters there and that, it is mass, length, and time. And then the last thing, diameter, is units of meters, which is length. Okay, so those are the units of the 1, 2, 3, 4, are we missing one? Density, thank you, yes, right. Density is units of kilograms per meter cubed, so that's mass divided by length cubed. So we're going to go through a process of combining all these together and trying to form dimensionless groups. I'm going to make a table where we've got the variable and then the units of a variable or a variable group. Okay, let me go over like this. So there's going to be the drag force as our variable, velocity, density, viscosity, and diameter. Okay, so the units of force, we previously determined that's mass, length, divided by time squared. The units associated with velocity, that is length per time. The units associated with density, mass per length cubed. Viscosity is mass divided by length time. And then lastly, density is, diameter is length. Okay, so what I want to do here in our beginning, in stage one, we have the variables that are known to have some relationship with each other. This is just, there's an equation. We don't know what the equation is, but these are all the variables that are going to be in it. And the units associated with those. In step two, we want to try and combine the variables together to simplify the units. So from 1 to 2, my strategy, as I'd write it out in English, combine variables to simplify units. So here's what I mean by that. From 1 to 2, I'm going to use diameter to cancel out any place length is in the units of a variable. So for example, if I have the force divided by diameter, that looks weird. Force divided by diameter. That's my variable. What's the units of that grouping? If I have force divided by diameter, what's the units that are left over? It's going to be, right, m divided by t squared. So this unit grouping is simpler because now it doesn't have the length parameter in it. Okay, so how should I combine velocity and diameter to simplify the units of this velocity term. Same thing, just divide. So v divided by d will give me units of 1 over time. All right? Now what about density and d? How should I combine density and d in order to make it so the units I want is just mass? Right. Density times diameter cubed. That grouping will just leave mass units. Viscosity, I'll do viscosity times d, and then that'll leave me with mass divided by time. And then what I do here is I leave it blank. I'm going to put a line in like that to indicate I've already used up d. You know, d is now found in the other variable groups, and so I don't have to keep listing it as one of my rows. So what's the trend? What am I going to do in going stage 2 to stage 3? I'm going to pick one of the units. It doesn't matter which, actually. It doesn't matter if I try to cancel out time or I try to cancel out mass. There's more than one right answer in the way that you do these. I think, so in 1 to 2, what I did was I combined the variables by using length. So I'm going to put here in margins use L. Okay, from stage 2 to stage 3, what I'm going to do is I'm going to use the variable grouping density diameter cubed, because that's where I have mass. I want to knock mass out wherever it's found in the units. So if I had force, density, diameter to the 4th, so in other words, if I divide this grouping by that one, then it'll cancel out the mass from the units. It will just be 1 divided by t squared. So this is the one that I'm using is this one. So I'm using this grouping. No. I marked the wrong one. This grouping. Density, diameter cubed. Now, it doesn't do anything with this next row, velocity divided by diameter, so it stays the same. I haven't done any combinations because it only has units of time right now, and I'm not canceling out time. Right now, I'm trying to cancel out mass. So then the combination of this and this to get rid of the mass, it's going to be the viscosity divided by viscosity times diameter divided by density diameter cubed, and then that'll leave me with 1 divided by t. And since I've got diameter in the numerator and the denominator, I'm going to erase this one up here in the numerator, and instead of d cubed, it'll be d squared. Okay, and my final stage, stage 4, I'm going to have variables and units. Obviously, I want to cancel out time. It's the only variable that's left, so I can use either one of these that has time in it. I'm going to use v divided by d. So I'm going to use up this one. I'm going to incorporate these variables into the other two groupings. So 1 divided by t squared, how do I combine this grouping and this one so that it's unitless? Well, I'm going to have to invert it. If I have d divided by v, then that has units of t. I'm going to have to square it. So it will be f divided by density v squared d squared, because there was d squared in the numerator, but it canceled out the d to the 4th that was there, and it will be unitless over here as a grouping. And then how do we incorporate this into the last remaining group? Same thing, we have to invert it, so it's going to be viscosity divided by density, velocity, and diameter, and unitless. It's like Sudoku. The first time you try it, it doesn't make any sense, right? This doesn't make any sense either until you actually have to start working the puzzle yourself. And that's why I gave you in your handout there, the last page is a handout where you can try your hand at the dimensional analysis game. So there's two different parts here. First of all, I'd like you to try calculating the dimensions of the variable groupings that I've provided, and then take a minute to do that first part, and we'll go over it just to warm you up to the idea of combining units and so on. And then I'll ask you to start on phase 2. Okay, so go ahead, for these three boxed in unit groups, find out what's the overall dimensions of that grouping. Okay, what about this first one? Density, velocity squared divided by 2. That's going to be kilograms, meters squared, cubed, squared. So kilograms per cubic meter for the density, and then velocity is meters squared per second squared. So that is kilograms per meter second squared. So that is, as we'd write it in terms of m, l, and t, that's mass, length, times squared. Everybody already get that one? The next one's kind of tricky though, shear stress. The shear stress divided by density, and all that's in the square root. So it is newtons times meter cubed divided by meter squared is kilograms, and that's to the 1/2 power. Okay, remember we have to expand out the newtons into kilograms meters per second squared, and then there is the meters cubed that was already there from the density, and the kilograms that's there from the density, and it's still to the 1/2 power. So we can cancel out the kilograms. We've got meters to the 4th divided by meters squared, so that is going to go to meters, hold on, I missed something here, these meters, right, forgot to carry those. What am I doing here? Kilograms meter per second squared. Okay, that's from the newtons. Yeah, the meter squared that was there from the shear stress, because it's newtons per meter squared, right. So then the meters to the 4th cancel the meter squared, and it's second squared. That's to the 1/2 power, so it's meters per second is the units of that group. And then the last one is unitless. We've got discharge, angular speed, diameter cubed. So that has units of cubic meters per second for the discharge. That's the units of flow rate. The units of angular speed is seconds to the -1 power, and then diameter is meters cubed. So the seconds multiplied seconds to the -1, that cancels out immediately, and then we've got meters cubed divided by meters cubed, so it is unitless. All right. So with our remaining time, I'd like you to take a crack at I don't know. I'm trying to balance here. Should I have you do? Yeah, I'm going to just have you do the dimensional analysis. So fill in that table using the same procedure that, that we followed here, where you find the groups and try and combine them. I'm going to put the solution on screen so you can see if you've got the right approach.